Welcome to the Chapter 25 Homework Solutions for AP Physics 2. So there are a number of problems here. They were a little more pluggish and chuggish than usual, but I'm hoping that they're going to be something that's helpful just to start knowing how to recognize what formulas to use. So this one was basically saying what voltage or EMF do we get if we have a shark which is moving through the water at a speed of 1.5 meters per second. The Earth's magnetic field is 5 times 10 to the negative fifth Tesla, at least the perpendicular component is, and the width of the shark's head is 0.85 meters. So that EMF is a very small amount. It's 6.4 times 10 to the negative fifth volts, using the formula equals BLV. But the interesting thing is those sharks, those hammerhead sharks, use that to detect changes in the magnetic field, I think, around them, under the surface of like the sand at the bottom of the ocean, to find food, which is really cool. This one, problem 4, you have a rod here that's pulled to the right, to the left. The velocity is to the left at 3.5 meters per second. 0.15 meters wide like this. Field strength is given. Resistance to the rod is given. It's being pulled at a constant speed. So the poles to the left for the magnetic force will oppose that, acting to the right. To find the induced current in the rod, we need to use V over R. In this case, it's EMF, which is voltage over R, BLV divided by R. So again, we've got 1.4 Tesla, 0.15 meters, 3.5 meters per second. The resistance is 0.65 ohms. So that comes up to, that gives us 0.735 volts. It gave us this resistance of 0.65 ohms, so that's 1.13 amps. Now, and that's heading down this wire, which would be clockwise. Why? Well, if you look at it, our magnetic flux is decreasing if this rod is being pulled to the left. So therefore, to oppose a decrease in x's, we need more x's. And therefore, that would indicate with the right-hand rule, the right curvy hand rule, that we would have a clockwise current. For part B here, it's asking you to figure out the amount of the force needed to keep this at a constant speed. Recognizing that these are equal, I do think that free body diagram is helpful. So this pole force is equal to the magnetic force. Well, the magnetic force on the wire we can find by using B times I times L, and that's 1.4 Tesla, 1.13 amps, 0.15 meters. So that's about 0.237 newtons. P10 is asking for the net flux. This case part we have a flux into the page. This part we have flux out of the page. The areas are the same. They're both 0.2 times 0.2 meters. But here the field strength is twice as much. So basically what I can do is I could take 2 minus 1 and say I have 1 net Tesla field in a 0.2 meter squared area. And that's kind of what I did here. I ended up getting 0.04 Webers. And if you remember, a Weber is a Tesla times a meter squared going into the page. P15 I did on the board. The formula for this is on page 890. The EMF is change in flux per time, but if you have a coil with a bunch of turns, you multiply that voltage per turn by the number of turns. So we get we were told that it's 0.1 Tesla changing in 10 milliseconds, so that's 10 Tesla per second. The area, pi r squared. If this was a diameter of 2 centimeters, it's a radius of 0.01 meters. So that's the radius. So we end up getting 10, I don't know why I have all the 0 there, times, oh, that's why, because it's 1,000 times 10, duh. So it is 10,000 times 0.000314, so that's 3.14 volts, or pi volts. Speaking of pi, what's your favorite holiday pie? Answer in the comment section. Oh, that's a YouTube video. Answer by sending me a text on Remind. We'll see who actually listens to this. Problem 17 deals with the magnetic field changing in an area here, and it's asking you to find the current in it. The resistance of all these wires or loops is 0.1 ohms. So here it told you that the field strength was increasing at 0.5 Tesla per second. Here it's decreasing. But here it's coming out of the page, and there it's going into the page. So essentially those are going to have the same effect, because an increasing field out of the page means we're going to oppose that by creating X's in here, or field into the page in here. In the same way, decreasing field strength into the page means we're going to oppose that by X's into the page. So When I look at this, this is my formula for change in flux over change in time to find voltage, 0.5 Tesla per second. The area of this is, if I do pi r squared, 0.00785 square meters. That gives me 0.0039 volts. As you can tell, I screwed up by moving a decimal the wrong way. So in this case, I've got E divided by R, 0.0039 divided by 0.1 ohms, so that's 0.039 amps. I think they said that's 39 milliamps. So in this case, for A, we're going to get the voltage mentioned and the current mentioned. In a way, I should circle that, in a way, there we go, that is causing a clockwise current. So clockwise current in both these cases will oppose the change in flux that's happening. There is no voltage, no current here because this loop doesn't have any flux in it. The field is going into the page and the loop is faced as shown. For problem 20, you had 150 milliamp counterclockwise current, 0.08 times 0.08 area. Resistance of the loop is 0.10 ohms. It says for a counterclockwise current, then what would the field strength be increasing or decreasing? So to get a counterclockwise current with the curvy hand rule, I could recognize that that is going to be causing that is going to be created, rather, by dots forming, and dots are going to pose an increase in flux into the page. So in this case, the field strength must be increasing. If I'm given this current and I know this resistance, I should be able to go back and figure out the voltage. It's 0.015 volts. And if I know the voltage, I can use this change in flux divided by change in time to help figure out this area, because it was given that this is I'm basically trying to find this change in field strength per time. So I know the voltage. This is something I don't know. This is the area. So I get around 2.3 Tesla per second as the rate at which the field strength is changing. For problem 21, I'm basically told the rate at which the field strength is changing. I can find the area again pretty easily. It was 0.5 Tesla in 10 milliseconds, so that's 50 Tesla per second. So if I know that this is changing 50 Tesla per second and the area over here is 0.04 square meters, I get that I have an EMF generated of 2 volts. But if I look at this and it indicates to me the field strength is increasing, then I would oppose that by having X's in this area, and that would cause the EMF to be pointing in a clockwise direction. We already have 9 volts in the clockwise direction. So since these are both pointing the same way, I would simply add the 2 volts and the 7 volt and the 9 volts. It gives me 11 volts divided by 20 ohms, and that's how I get my 0.55 amps. If I was told that this field strength was decreasing, then this induced voltage would be pointing the other way, and I'd have 9 minus 2 volts divided by the resistance. Going to 65, which is the last one. You've got a 0 resistance wires here. This wire does have resistance. It's 10 centimeters length, going at 0.5 meters per second due to a push. Resistance here is 2 ohms. It says it's going at a constant speed. So once again, we have this free body diagram to indicate equilibrium condition. So to find the pushing force, we need to find the current going through the wire, and that'll tell us the magnetic force. So I set those equal again based on that free body diagram. I'm going to use this E equals BLV to get the voltage, and then use Ohm's law to get the current, and then use the Fabel to get the force. And the force on this wire, and this is a magnetic force pointing to the left because that's going to oppose the change in flux, is 0.000625 newtons. Well, if I want to find power, one of the formulas to do that is force times velocity. Well, I know the force and I know the velocity. There are other ways to do that, but that's probably the most straightforward mathematically. When I think about the power dissipated in the circuit, we know that this is 0.025 volts, 0.0125 amps. You can either do V times I, or you could do I squared times R. Either way, comes out to the same value. So we have the same power to move the wire is dissipated in the resistance, which is good because, hey, energy is conserved and power is a rate of energy transfer. So hopefully this helps. Hopefully it makes sense to you, and thank you.